Welcome everyone. Today we'll be talking about some CST basics. Mainly the focus will be on metamaterials and metamaterial based sensor for terahertz and gigahertz range. So my target is not to teach you guys about how to use CST or how to design antenna or things like that. My courses will be focused on only metamaterial and metamaterial based sensor, and I'll be showing you all the settings, mainly the most of the settings that I use more often. I'll be showing them, and I think it will be easier for you to follow. And if you are working on metamaterial and sensors, then this video might save you some time without wasting, learning everything. Just this video will be concentrated on only for metamaterial. So let's begin from the things we'll be covering. Mainly how to prepare CST for terahertz range and gigahertz also. Then we will also talk about metamaterial sensors, like if we want to make a sensor this kind of in for this kind of setup, what should we do? How should we prepare the sensing environment? And then we also will show you how should you prepare the CST for a transmission line based sensor setup. Actually, I will not design any metamaterial, or I will not design any experimental setup into this video. I will just show you how we can start the CST for specific purposes. Like if I want to make a sensor that will be a like sandwich structure, then what are the settings that I should have in my CST? Then I will go for the designing. So the designing part will be a different issue, a different video, but this video will only cover the settings or pre-settings of the CST. And I also will show you some basic concept that will help you to simulate different CST simulation environment, so that you don't have to find every video for a small details. For every sensor setup, you usually need this kind of settings very often. So this video will also include these topics. I'll just show you how to use these tools of CST. I will not make a final design. I'll just show you how we can use them. And later on, maybe in another video, we will talk about how we can design actually the settings. So later on I will explain these papers. Those are my papers, and so I'll go to one by one. I will explain every paper, so how the things have been done, and what are the techniques that we have used. As I will not show you any simulation, any measurement. I will just cover the simulation part and the design part. But this is for this will be another playlist. For today, we will be only concentrating on preparing the CST. So without further ado, let's go to CST and show you from the beginning. So first, we will prepare CST for terahertz range. Remember, it is not a very long video, because we are not designing anything. We are just preparing the CST. So every part, maybe this one slide will take like 2 or 3 minutes, and then this one will be another 2 or 3 minutes, and this one, and so on. So let's go to CST. Let's close this one. So here you can see this is the beginning interface of CST. Let's make a new template. We are working with microwave and RF, so we will select this one. Okay, so now we are working with terahertz, right? So these settings will be used for terahertz. Let's show you how we should Let's go to periodic structure because we are designing metamaterial. As we are designing metamaterial, we will go to periodic setup. Otherwise, if we are going to design an antenna or like a transmission line metamaterial, then you should go into the antenna. But we are not making any transmission line sensor or like any antenna. So we'll just make a metamaterial structure, a unit cell. So we will go to periodic structure. Actually, you can also do the things in here. Also, you can do the things of everything here, but it's more convenient as more settings are already predefined for you. So we will make unit cell. So we will go FSS metamaterial unit cell. What does it mean? Frequency selective surface or the metamaterial. This is for I mean metamaterial unit cell designing. We can also use all of them, but like I said, for some predefined settings, we'll go there. And next, we will select phase reflection diagram, and after that we will select frequency domain because most of the simulations, there is two things actually. Most of the papers and most of the work that you see is in frequency domain. You can also use time domain, but first of all you have to think about your license. If the if you have the time domain license, then you can simulate in time domain, otherwise you cannot. And then in frequency domain it is more easier for us to understand because it's more common practice. So we will select frequency domain, and after that, as you can see, we are working on terahertz, so we'll select terahertz. Nanometer is okay, millimeter, micrometer is also okay. So nano, actually it is up to you. So next, okay, here you can see that my definition are in wavelengths, in terahertz, in unit cell, in this step. I mean, like FSN metamaterial unit cell. CST by default select the frequency, or I mean the parameter is in wavelength, but you can also use frequency. Then you will just specify which frequencies you are using. But as we are working with terahertz, it is a more common practice to show the results in wavelength. That's why we'll go with the wavelength. So let's say we are making a metamaterial for optical range. That means it will be from 300 nanometer to like 1000 nanometer. Let's go and see the things. Okay, so optical range is from uh, so from 100 to, I mean, visible light is from 100 to 380 to 7, almost 800. So we will just take, okay, this is nano. Okay, so let's convert. I'm just converting is for your convenience. Actually, you know the calculations. So for 3, we just, yeah, and then we will, let's say 1000 for 1. So let's go do the settings in here. Give, as we are using then 0.3, and here should be 1. Okay, so, and here E field and H field and far field and so on, you can select them if you want, but you can also set them in later when we do the simulation. But if you want to select those things, that means for your first simulation, the CST will automatically show you E field and H field result, and CST will ask some points. So you will, if we say 0.3, that means CST will show the field for wavelength 0.3, and 0.65 CST will show E field and H field at 0.5 nano, I think, micro wavelength, and also for 1000 nano. Okay, so if you want more, you can select, you can just add them. Like if you want at 7, you will just like this. So you can do it like this. So if you click next, CST will by default create E field and H field monitor on those frequency ranges or those wavelength ranges, and then it will automatically show you the results for them. But if you don't do it here, like let's say we will not do them, it's totally fine because you can do them later on in the process. So another thing we will do is as we are doing, as we are making a metamaterial, we will need absorbance, and actually metamaterial observer, for observer we will need absorbance and transmission and reflection. So we will actually, we can do it later also, but we will do it from the beginning. Okay. So let's go to the next. Everything is the, you don't have to change anything. It's, if you want to change the name, you can change the name. It's up to you. So here are your parameters. So let's finish. Okay. So this is how you prepare CST for your metamaterial for terahertz range. Okay. So if you don't want to, if you want to design a metamaterial for not terahertz, let's say gigahertz. So what are the steps that you have to follow? Actually, both steps are almost the same. You just have to change the frequency ranges from terahertz to to gigahertz, but all other settings are same. But still, for your convenience, I will do it again. Close. Let's start from the beginning. New project, and then periodic structure and inertial. Okay. Phase reflection. Okay. Time domain, frequency domain. Okay. And then we will, as we are going in gigahertz range, we will say millimeter, micrometer. I always forget this kind of word, micromilli. Sometimes I just mispronounce them. Okay, let's go to the next step. So those things, in general, you don't need them, but you can also use temperature shifting in CST. I will show it later on. Okay. So here we can see the results in wavelength. So you can go in frequency also as well. Then let's say we are working in 1 to 6 gigahertz. So we want our result E field and H field at 1 gigahertz and 3.5 gigahertz. Let's say I want in 4 gigahertz also. Say 4. Then let's say I need in 4.5 also. So this is the way, and we can also calculate. This is something that we don't have to do, but I'll show you the difference. Okay, so here is our setup for a metamaterial in gigahertz range. So as you can see, as we have selected far field monitors in some frequency ranges, so we can see that we have a E field monitor at 1 gigahertz and 3.5 gigahertz and 4 gigahertz and 4.5 gigahertz and 6 gigahertz. Those things are here because we said that we need those results as we are starting our simulations. Okay, so this is how you prepare CST for your metamaterial design in gigahertz range. Let's close this one. So now we will start looking over the sensor setup using metamaterial. First, we will see the setup for this kind of sandwich. You can say in many papers you'll see this shape is being called as a sandwich setup. So we will show you how to design this kind of thing. So basically the concept for metamaterial sensor and metamaterial sensor as a sandwich layer is same. You just put your test object on top of the metamaterial and then do the simulations, and then later on change the property of the test object and see the result in the metamaterial performance. By this way you can see how the sensor is how the metamaterial is working as a sensor. So let's go to the CST. Mm, so here you can see this one is a metamaterial based sensor, and it is now in the condition of sandwich sensing model. So here you can see that this part is the metamaterial with the substrate, and in the middle the transparent layer. Let's say this one is a layer of oil. I think I have used oil, right? Yeah. Oh no, soil. I used soil, and then the behind there is another FF4 layer. I just put it because I want to put the sample. You need a sample holder, right? So if you make a sample holder using FF4, then the experimental setup will be like this. That's why I designed the structure like this to better replicate the scenario in the simulation. So as you can see here, uh, in actual scenario, you can see that there is the metamaterial and this is the test object, and then this is the holder. The holder is holding the everything. So you can also use another layer, but we didn't use. We used only three side of the box. Then another side, the fourth side was the metamaterial itself. So we did not use any plastic in this side. Just put the metamaterial here. That's why in simulation we did not you don't see any layer of another holding layer. You see only one layer. So we just design the metamaterial like this, and then also the holder, and then we in the middle we put the sensing material. This is how we simulate metamaterial based sensor setup for like sandwich structure. And you can see the simulation setup is pretty much the same. We used boundary conditions, and the everything is same. Here you can see that we used two ports. Why we did that? Because we are planning to measure in T and T mode. I will show you those things in later on. Okay, so just a side note. Okay, I mean, how I can moving this thing, because I am selecting the rotating function. But so after that, I can see that this is the transmission line setup. How we are going to simulation transmission line based metamaterial. Actually, transmission line based metamaterial is similar to the antenna. First, you design a transmission line, then you place a metamaterial or a resonator near to the or in a desired position that you want near to the transmission line, and then you observe the response of the transmission line itself. So here you can see that this is the transmission line, slightly modified transmission line, and on top of that one, this is the resonator. Here you can see that this is the resonator and this is the transmission line. So we connected two ports on the both side of the transmission line. Then we measure the response, but we are using the metamaterial as the sensor. There can be many other techniques to do this, but this is one of the way of doing it. So the difference is here we used waveguide ports. Uh, we didn't have to use any SMA port, but in transmission line we will use SMA port. So the simulation structure will be, the simulation setup will be different. So let's go to CST. Here you can see this is the transmission line based metamaterial. Uh, Let me show you how we design the um, transmission line setup. Okay, let me first copy everything, make a new project. uh, this is transmission line based antenna, so we'll go transmission line based sensor, so we'll go to the antenna and patch next frequency domain. Everything is fine. We can define them later on. It's okay. I will not show you the whole designing process. I'll just paste them here. And yeah, this is the sensor. Now we can, for simulation, we will add ports here. We can, I will use discrete port, so I can select it here and there. It doesn't actually affect, but it looks good. That's why I did this. And then another port will be on the other side as we are measuring the S21 parameters. So yeah, now this sensor is ready for simulation. I will just define the frequency. Let's say 1, 2, 3. Okay. So now if you start the simulation from here or from here, you'll get the response of the transmission line, the metamaterial. The concept is we place metamaterial near to the transmission line and then we see the response of the transmission line. Here you can see that this is the actual setup. This is pretty much similar to the measurement setup. There is the pipeline and there is the actual pipeline. So we flow some liquid through the pipeline. So in a practical scenario, we flow some liquid through this pipeline. So this is how the simulation looks like. Okay. Uh, Next is some parameters. Okay. So what is parameter swap? Parameter swap means we set some parameter, then we change those parameters sequentially. Like if here you can see that the bottom, the ground layer has some defects, right? There is a gap. So what is the optimum length for this gap? How we decide this copper layer should be 12.5 millimeter long and the gap in between should be 15. How we can do this? Actually, we there is a settings in CST. If you go to the home there, then go to parameter swap. Uh, you can see that this opens up a dialog box. Here we can change the parameters. So first you have to define some parameter during the designing. For the sake of understanding, I will just delete one copper layer and redesign it so that you can understand what I am saying. Let's say, yeah, this one I will delete. Sorry. Okay. Okay. So now I will make a copper layer. Mm. Okay. So let me first define the thickness, because we are not going to change the thickness, so we will not use any parameter or any variable. Parameter is the kind of like variable, so we will not use any variables. um, so we have uh, thickness. Now we will not change the height of the copper layer. We will just change in one direction, okay, for simplicity of better understanding for you. Okay. So we'll not change any y direction. So this is we're not gonna change, but we will change this one. So this is the minus 20 y. This one is 10. This one is another 10. That means this one is, we are on the back. So remember, this is the front. Let's see front. Okay, this is the front. and let's go to the back. This is the back. So this will be the negative side, right? Okay. So here it says that it will start from -20 and it will go up to -10. Instead of doing this, as we are changing this side, we can say that no, we will make length of ground LG. Okay, it's totally up to you, whatever you want, right? You can write anything. Okay, let's review. We have to give some value because CST doesn't know what is the value for LG. So like before, we are going to use 10. Okay, okay. So you see there is no change because the value of LG is same 10. So you see here value of LG is 10. Okay, okay. Now okay. So if I go to parameters of new sequence, new parameter, you can see the LG. Okay, if you have 10 parameters, you'll see the list of 10 parameters. Okay, so now the value is 10. So if I want to move this copper layer to the front side, I would have given like let's -5. Okay, so the range is from 10 to 5. And how many samples we're gonna simple? Let's say 5. So what it will do is it will simulate 5 times. See, 5 times, and from in first simulation the copper layer will be like this. After that it will increases its length, then after a bit more, then a bit more, and then a bit more, and so overall it will simulate 5 times and give you 5 different results for different length of the copper layer. Okay, so you can change, you can check if your values are right. To check, click check. You can see the simulation is showing that how the sequence will run. Okay, so and so you will get your 5 different result in this 1D result. It is not only for the length and width, you can also change material properties also. Like if you want to change the dielectric property of this copper layer, I mean, I'm just giving it as an example. Let's say I want to change the dielectric property of this water layer. So what I will do, I will go to the water layer and then right click, change property, edit material properties. So you can see the value of epsilon is 78. I can just write EPS, some kind of value, and then give the value of 78. Let's say give, okay, delete, okay, apply. Okay. So now if I go to parameters up and go to new parameter, you see that there are EPS. Okay, this is another file. That's why there are many other variables, but you see the value is there. So you can change that one also. So this is how you use the parameters of function, and then we will show you okay, orientation of polarization. Okay. So okay, first of all, let me explain what is polarization. Polarization. Remember this course is for the beginners, so I'm breaking down everything. Okay, so polarization is like this. We are considering the metamaterial roughly like this horizontally. Which angle is changing? The polarization angle is changing. Okay, okay. So if we don't do that, we rotate it like this. Now the oblique angle or the incident angle is changing. I will explain the scenario a bit in detail. Let's take a screenshot. Okay, so so if we rotate the structure like this and say the material, the light is, yeah, light is putting on top of this one. In the respective of the light or the electromagnetic wave, the sensor is changing its, the metamaterial is changing its polarization. But if we rotate the sensor like this, so the light is coming here. So you can see that if I rotate this one, maybe the light would have gone like this. But if I change the direction a bit more, but for now it will also, this angle will be changed, that the reflection maybe will go like this, the angle will increase. This is called incident angle, the way the wave is falling on top of the metamaterial. Okay, so how we change the those things? We change them by CST by default creates two variables for polarization and theta. If you go to parameter swap, so whenever you open a project in the Metamaterial setup, the steps we followed in these two slides to open a project similarly, you'll see that there are two by default parameters here, pi and theta. Pi and theta, we did created them. Pi and theta was created by 16 itself. So here you can see we will change pi from to 180 got to 360 degrees. What does it mean? Let me show you. Yes, let's say 6 simulations. So I will delete. So now check what will happen. The metamaterial is, the wave's angle is changing. Okay. Similarly, if you go to parameter swap and new and go theta, so you can use 0 to 89. You cannot use actually 90 because that way CST will not allow you to run the simulation because when you have 90-degree, nothing propagates through this metamaterial, so CST will show you an error and it will say that theta degree 90 degree is not possible. Okay, so now we have completed theta and pi. Now let's go for T and TM mode. Okay, so T and TM, for T and TM mode, you should have more than one number of ports. Let me start from the beginning. Let's say from here. Okay, for it should have not one but two, because there will be two modes, and it should be for the both Z max and Z mini. Okay, clear results. Okay, so now we have 4 ports. If you go here, you'll see that there will be 4 and if you click on them, you see that there are 2 ports. Okay, so for T and TM mode, you just go here and details, go to details and see port 1 will be in T, A mode will be TM mode. You can just close them, but it will not work because I did not activated them. I mean, I only used two ports, so this there will be only two ports. So first port will give you uh, E mode result, and then the second port, the second one will give you uh, TM mode. So how the result will look, instead of having one S1 and S21 parameter, or one sets of result, you'll have two sets of result, and the results that you see for port 2 give uh, TE mode, and the port 1 will give you TM mode. For bending angle, bending means bending the metamaterial or the bending the specialized sensor to a certain degree, or if there is an circle, how much um, angular area the structure makes. So to do, let's see this design. This is a very simple design. So let's say we'll bend this to 10 degrees. So do that. To do it, we have to select the component first, and then go bend. Let's say we'll bend it cylindrically. Then here you can see will it's saying that how much will be the radius circle. Okay? So if you see that the one side of the metamaterial has bent a little bit, both click both sides, then it will bend both sides. So this is how you bend a material, and it also changes this one. So the bending will be uh, different. Let's say if review. So bending is a little bit less now. This you can the angle. It means that how much angular space there. So if there's the, that means it will 90-degree area. You see, from if this is the center of the circle, the angle from here to here is 90. You can say, let's say 45. Let's see how this. Okay. So now it is 45 degree. Okay. So this is how you bend a material, and after there is preparing new material. Okay. For preparing new material, we have to, let's say we want to say we use something other than the FR4 as a substrate. So this one is substrate. We can set any material from uh, sorry, and material. Say we want to use something that is not available in this library. So we should go here and new material, and we give the material uh, give the value, the electric value. Where you can find the value, you should find a paper or a database where you have different values of dielectric properties. Actually, you have to collect most of the data and fill them up, and finally make the material. Here you can change the color and change the transparency. So in general cases, if you are developing some sensing material, test material, epsilon is enough. But if you're making a substrate, should get much data as well is better. So this is how create a material, and then it's and it will be there. You see, this is a new material. Here you can see the material is here, value shown in here. Okay. Now the fabrication. If you want to fabricate a metamaterial or a cell. It is the processing is like all like similar for entry. So you go and select a face. Let's say we are in the font. Usually we use dfx file, dxf file. So you will click here and the dxf file. Otherwise, if you do not select any layer, you will find not a proper DXF. Sometimes you see that this option is not activated. So let me follow the rules. Okay, so you see, even if I selected the top layer, is showing me the bottom layer. Why? Because my axis referenced in the bottom layer. So what we have to do is clear everything. Now select a layer, local axis, select this. So now the center is here. So we will do it. So now you can see that the layer I want to select is selected. Let's say I want to take the subject. So let's pick this and oh, I forgot to select the layer. Okay. Now it should be fine. Yeah, now you can see that we have selected the substrate layer, upper side of the substrate layer. Now just uh, press enter or escape anything, give it a name like font. So now you have your DXF file. So those are basic settings that you need to learn for designing and simulating sensor and metamaterials. Hope this video will help you.